Hi there, let's work through a couple of these examples of questions where we're being asked to dissociate a salt into the ions that make up that salt and then calculate the ion concentrations. Here's an example that we worked out for this calculating molarity assignment as one of the examples. Let's actually work it out together here. So we've got a 0.03 molar solution of magnesium phosphide, and we're given the molecular formula for magnesium phosphide. So there's the salt. So we're going to go ahead and write a balanced reaction equation showing this salt breaking into its respective ions. So the first thing I'm going to do is I'm going to write my salt on the left-hand side here. So I've got magnesium, and I can see that magnesium has a little subscript 3, which tells me that there's 3 magnesium ions in this compound, and phosphide, or phosphorus here, has a little subscript 2, which tells me that there's 2 phosphide ions attached to 3 magnesium ions. Because it's a salt, I'm going to use the subscript, or the subscript for the phase S, meaning that it's a solid. And then I'm going to have an arrow, and I'm going to break this into the ions that form it. So remember what I said, the little subscripts here tell us how many of each ion are present in the compound. So there's 3 magnesium ions, and that 3 is now going to be written in front as a coefficient. Because now that I'm breaking it apart, I'm going to break the ions up, and I'm going to show how many of each there are using a coefficient in the front. So I'm going to put in the symbol for magnesium. Now it is an ion, and this, leaving it like this would be incorrect, because leaving it as just Mg means that that's a neutral atom or a neutral element, and in fact it's not, it's an ion, so it needs to have a charge up here, and we need to look at a periodic table of elements to find the charge on magnesium. Now I could do a little bit of reverse swap and drop here too, and take a guess that it probably has a 2+ charge because it has to balance with the phosphorus here, but it's always best to look it up on your periodic table of elements and double check what the charge is, and it does have a 2+ charge. So there we go. So 3 magnesium 2+, and now this is an ion, so I'm going to use the phase of matter aqueous in brackets as a subscript to show that this is an aqueous ion, meaning that it's in solution. Okay, what's the other half of this? I've got 3 magnesiums, and I've got 2, we'll put that coefficient 2 in front, 2 phosphide ions. So the symbol for phosphide is P, and again I need to have that charge to make sure that I show it's an ion. And so I'm going to look up phosphide. I'm going to look at phosphorus on my periodic table, and I'm going to see that it has a little charge of 3+ when it's in ion form. Sorry, 3-. Okay, and again, this is aqueous because this is an ion. So we've balanced this reaction out. I've got 3 magnesium ions with a 2+ charge for every 2 phosphide ions with a 3- charge. And when those come together, they form the salt magnesium phosphide. The last step here is to figure out what's the ion concentrations of my magnesium and my phosphide ions. If I'm starting with 0.03 molar, okay, of my salt. Now remember our mole ratios. So we've got a 1 to 3 to 2 mole ratio. So that means that for every 1 mole of salt, I'm producing 3 moles of magnesium 2+ ion. And so I can go ahead and multiply this number right here by 3. So 0.03 molar times by 3 is going to give me 0.09 molar. And the same thing goes for my last ion. The mole ratio here is 2, so for every 1 mole of salt I produce 2 moles of phosphide ions, and so I can multiply that 0.03 by 2, which is going to give me, 3. This should be a 3. My writing is messy. And so my answer here is going to be 0.06 moles per liter, molar. Okay, I can leave it like this, or if I want to be really clean and tidy, I could write square brackets, which mean concentration of magnesium 2+ is equal to 0.09 moles per liter, or molar. And the concentration of phosphide ion is equal to 0.06 molar. And there are my answers. We'll do one more example if you're feeling like you'd like to see one more. Okay, let's do one more example together, and I wanted to include one where we have a salt that contains a polyatomic ion, which is going to be this guy right here, the nitrate, NO3. Same thing, let's start with our salt on the left. I'm going to write out the formula, Ca nitrate NO3, and I've got this little 2 outside the brackets. All right, and that's a solid because we're saying it's a salt. And it's going to form, well, what ions will this form? I know calcium is a metal ion, and I can look calcium up on my periodic table and look up the ion charge when it forms an ion, and it has a 2+ charge. Okay, let's come back here to our formula for a minute, and notice that I don't have a subscript after the calcium. There's nothing here, okay, which means, in fact, if there's nothing shown, it's just a 1. And so if I want to, I could put a 1 in front of that calcium. All right, that's an ion, so I'm going to write AQ for aqueous, meaning that it's in solution. And my second ion is this polyatomic ion right here. Remember to be careful when you're writing out the ions from a salt. When you see more than one element, that means that part of this salt is a polyatomic ion. And you want to get out your chart of ions and be looking for part of this. And it's easy when you recognize that calcium is a metal ion, because that means that the other half of it, the NO3, must be a polyatomic ion. And if we look it up in our table of ions, we're going to see that this right here is called nitrate, and it has a charge of -1. Okay, minus. The brackets around that polyatomic ion tell me that there is more than one of these, and the little subscript here tells me there's 2 of that polyatomic ion in this compound. So I'm going to put that 2 in front now as coefficient because it's broken apart. And again, I'm going to use the subscript aqueous to show that it's an aqueous species. It's an ion. Okay, so I have a balanced reaction for the dissociation of calcium nitrate, and the last step that I have to do here is determine the ion concentrations. I'm told that I'm starting with 0.01 molar solution of the salt, so I'm going to use those mole ratios to figure out what the concentrations of ions are. And it is a 1:1 to 2 mole ratio. So it's going to be the same for the calcium. It's going to be 0.01 moles per liter. And for the nitrate, notice it's a 1:2, and so it's going to be 2 times 0.01, which is 0.02 moles per liter. I'll leave it at that. I just wanted to include one more example for you. And you should be doing some practice with the calculating molarity assignment, and hopefully by the end of that you feel like you've really got the hang of this. Don't forget to use your periodic table of elements and look up ion charges, and also use your polyatomic ions chart in your data pages, because you're going to need that for all of the polyatomic ions. Good luck!